Right, so in this video I'm going to have a look at different ways to determine rate experimentally with a specific focus on colorimetry. Before we look at colorimetry, we'll just have a brief look at the two more basic methods of determining the rate, which you should be familiar with from GCSE. So both of these methods rely on you producing a gas as one of your products. The one I've got here on the top, I've got sulfuric acid reacting with magnesium. That's an acid reacting with a metal, so I'm going to produce hydrogen gas. And what I can do is I can attach a gas syringe, and as that hydrogen gas is formed, it's going to escape the flask, enter the gas syringe, and I can collect the hydrogen gas as it is formed. Now, just collecting that hydrogen gas does not allow me to calculate the rate. I need to see how quickly that gas is being formed, so I need to have a stopwatch, and I need to record the volume of gas at regular intervals. So at 30 seconds, how much gas do I have? At 60, at 90, so on and so on. If you don't record at the time, you're only going to be able to record volume, and that's not enough to calculate rate. Similarly, at the bottom, I've got a reaction between marble chips and hydrochloric acid. Marble chips, that's calcium carbonate, so you're going to produce carbon dioxide gas. And because of the law of conservation of mass, the reactants and the products, the mass should be unchanged. But in this reaction, because you're producing carbon dioxide, a gas, one of your products is able to escape the flask, and you will see that mass decrease as the carbon dioxide escapes. Again, just recording the change in mass is not enough. You have to do the change in mass over time. So again, at regular time intervals, you would have to record what the mass is, and then when you've got the mass changing over time, you can then use that to calculate rate. The top method only works in a closed system. Okay, you don't want the gas to be able to escape, you're trying to collect it. The bottom one only works in an open system. I know there's cotton wool there, but that's just to prevent the acid escaping, so the acid kind of spraying up and escaping. The carbon dioxide will still be able to get out through that cotton wool, and it will be able to escape. Both of these methods rely on the fact that you are producing a gas as one of the products. Not all reactions are going to produce a gas, and in that case, colorimetry can be used. So I've got a common example written here of a reaction that will use colorimetry. I've got a ketone, propanone, reacting with iodine to form the following products. And none of these products are gases, so I need a different method. So if we look at what colorimetry is, we don't need to understand the physics behind this. All we need to know is that coloured solutions are able to absorb light, and you can then track that absorbance. The more concentrated the solution is, the more light it can absorb. And you can use a special filter depending on the solution you've got. So in the question we're looking at iodine. Iodine is a brown colour. You'll use a special filter for iodine, and the more concentrated your iodine is, the more light it's going to be able to absorb. So if I have a look here back at my question, iodine is a brown colour, so I use a special filter that enables me to absorb that brown, it enables the iodine to absorb the light, and the higher the concentration of the iodine, the more brown the iodine, the more light it will be able to absorb. And what we'd expect to see is over the course of the reaction, as the concentration of iodine decreases, as it's used up, the colour of the iodine will fade, and as the colour fades, so too will the absorbance. So what you would do during this reaction, every kind of maybe 30 seconds, you would take out a sample from the solution and you'd run it through your colorimetry. And let's just say at the start, before you started the reaction, so at 0 seconds, you measured some of the sample and you saw that it had an absorbance of 0.8. And then 30 seconds later, you took another sample and you saw the absorbance had decreased slightly. And again, that's what I'm expecting. As the iodine is used up, the colour is going to fade and it's going to absorb less light. And then another 30 seconds later, I take a sample from the reaction, I run it through my colorimeter, and I see my absorbance is decreasing again. I'm able then to plot this little table. I've got time and I've got absorbance. But what I really care about when I'm looking at rate is I want to know how the concentration changes over time. At the moment, I've only got absorbance. I need to relate that absorbance to concentration. And in order to do that, I'm going to need to plot what is called a calibration curve. So to plot a calibration curve, I'm going to need to make up standard solutions. And standard solutions are just solutions where the concentration is accurately known. And the reason that the concentration is accurately known is because you're going to make those solutions yourself. So if I want to make up a standard solution, I'm going to use a volumetric flask. And in one volumetric flask, I might make up a concentration of iodine of 0.1 moles per decimeters cubed. And in another flask, I'll make up a solution with a concentration of 0.2. And in another flask, I'll make up a concentration of 0.3. And so on. So I'm going to make up these standard solutions. I know exactly what the concentration is because I've made those solutions myself. And then what I'm going to do is I'm going to take each of these solutions individually and I'm going to run it through my colorimeter. And what I should see is when I've got a low concentration, the 0.1, I'm going to get an absorbance, let's just say at 0.3. When I run the higher concentration through, the absorbance should be higher. And again, the higher the concentration, the higher the absorbance. But this time I have concentration directly related to absorbance. I know what the concentration is, and with the concentration of 0.1, this is the absorbance that I am getting. And I can use that then to plot myself a little graph. And what I would use as a control is I would take some water that had no iodine in it whatsoever. And because I'm using a filter specific to iodine, if I've just got water and no iodine, I should have an absorbance of 0. So down here, this would be my control. This would be water, 0 moles per decimeters cubed of iodine, and then 0 absorbance. And then what I'm seeing is as my concentration increases, so too does my absorbance. And I can plot myself a little calibration curve there. And then when I go back to the results that I got from my experiment, if I want to know, right, at 60 seconds, my absorbance was this, but what is the concentration? Then I just come down here, the absorbance is 0.4. I go to the absorbance on my y-axis, I come across my graph, I come down, and I'm able to see that if the absorbance is 0.4, my concentration must be 0.2. Again, at 60 seconds, I see, at 30 seconds, I see I've got an absorbance of 0.6. I'd have to, sorry, my graph's not quite big enough, but I would need to go to 0.6 on my y-axis, that's where my absorbance is. I go across to my graph, I go down, and I can work out what the concentration is at 0.6. And that can work for any absorbance, for any reading that you get when you're doing your experiment. If it was 0.35, you go here between 0.3 and 0.4, across, down, and you can read the concentration off. So your calibration curve allows you to go between the absorbance and the concentration. I'm going to have a look at one of the exam questions. Typically, they're not going to ask you about, they don't ask you about the colorimeter itself. You're not going to be asked to explain how it works in terms of the filters and the absorbing of light. They're typically going to give you some data, and they're going to ask you maybe to plot a graph and then to interpret that graph. So the same reaction that we've actually just looked at. A student investigates between iodine and propanone in the presence of an acid, and this is the method they use. So they're starting off with a known concentration of iodine. They know how much iodine they've got, and then they're mixing their iodine with their ketone and with their acid. Once they've got their reaction mixed up, they take a sample, put it in the colorimeter and start a stopwatch, and then they take different samples every 100 seconds and record the absorbance. First question is, why is it decreasing during the experiment? Okay, so you are measuring it's the iodine that is responsible for the absorbance of light. Because the concentration of iodine decreases as the reaction proceeds, the absorbance is going to decrease. So it decreases because the concentration of iodine decreases as the reaction progresses, and iodine is responsible for absorbing the light in the first place. It says down here that absorbance is proportional to concentration. Calculate the concentration at the start and after 500. Okay, so at the start of the experiment would be T equals 0. They told you the absorbance is 0.8. They want to know the concentration. You're going to have to go back up here to this information. Now they've told you that you're starting with a concentration of 1 mole per decimeters cubed, and I think a lot of you in this case would just take that value there and plug it straight into the table, and that wouldn't be correct. Okay, this is your stock solution. This is what you made up in your little volumetric flask. Your stock solution in your volumetric flask, you made it up to 1 mole per decimeters cubed. But let's look at the reaction solution. All right, you're only adding 1 centimeters cubed of iodine. You're then diluting it with 49.5 of your ketone and 49.5 of your acid. If you add all of those volumes together, you'll see the total volume of your reaction mixture is 100 centimeters cubed. Only 1 centimeter cubed of that is the iodine. So you are diluting your iodine by a factor of 100. That's the concentration of your stock solution. You take 1 centimetre cubed out, and you're diluting it by 100 in your reaction mixture. So instead of writing down a value of 1, I need to divide that by 100, 0.01. That's going to be my concentration of iodine at the start. Now, before I talked about using a calibration curve, okay, they haven't used a calibration curve, but they're telling you that absorbance is proportional to concentration. And once you know the absorbance and one concentration, you can use that relationship to work out the concentration for any other absorbance. So here I've got my absorbance going from 0.8 to 0.18. So to work out what that relationship is, I'm going to do 0.8 divided by 0.18. And when I do that, I get an answer of 4.4 recurring. Right, so to get from here to here, I would need to divide by 4.4 recurring. Okay, I'll show you that. It's 0.8. If I divide that by 4.44444 recurring, I'm going to get a value of 0.18. So if I need to divide by 4.4 recurring to get from this absorbance to this absorbance, then I'm going to do exactly the same with concentration. I'm going to divide by 4.4 recurring to work out the concentration at 500. So it's 0.01 divided by 4.44444, and I get an answer of 2.25 by 10 to the minus 3. So whatever I've done to this number, I'm going to do exactly the same to this number, and that keeps the relationship between them exactly the same, which is what I need. So it's similar to using a calibration curve, you just don't actually have the graph. It then asks you to plot a graph of absorbance against time and draw a line of best fit. So you've got these values here, you've got your times, you're going to plot all of those points and you're going to draw yourself a line of best fit. And what you should see is you end up with, I think, a straight line graph that looks something like that, okay? And then the last question asks you to use your graph to find the order of the reaction with respect to iodine and to explain your reasoning, okay? So on this graph here, I've got absorbance and I've got time. And we know that the absorbance is directly proportional to our concentration. So as the absorbance is decreasing, so too is our concentration decreasing. And on a concentration time graph, if you end up with a straight line, then that is indicative of a zero order reactant. The reason it's zero order, if I wanted to find the rate, okay, I would have to get the gradient. And because the line is a straight line, the gradient is exactly the same at every time point. That tells me that the rate stays exactly the same even as the concentration decreases. So I can see here that the absorbance is decreasing as concentration decreases, so I know concentration is decreasing, but I know my rate stays exactly the same. And the reason I know it stays the same is because my line is a straight line and the gradient is the same at all points. So if my concentration decreases but my rate stays the same, then I can say that the concentration of my reactant has no effect on the rate, and that is indicative of zero order. So I would write that it's zero order, and my explanation, I would say that the change in concentration does not change the rate of the reaction. Change in concentration of I2. So as the concentration of I2 decreases, the rate stays exactly the same. It shows that the concentration of iodine does not affect the rate of the reaction. That's essentially, that's your typical question on colorimetry. The other thing they can ask you, so there's just one multiple choice question here that asked you about it. It was just asking you to spot, where is it? Oh, crap, oh, wait, here it is. this one here. This one here relates to colorimetry as well. It tells you you've got zinc reacting with copper sulfate solution. It wants to know the apparatus that you would use. You do need to know what you're going to get in this reaction. The zinc and the copper are just going to swap places. Zinc is more reactive than copper. You get a displacement reaction. And copper sulfate is a blue colour, and because you're losing copper sulfate and making zinc sulfate instead, that blue colour is going to fade. And because you've got that colour change, colorimetry is going to be suitable. You can also work out that the other methods aren't suitable, so you're not producing a gas, therefore the balance in the gas syringe aren't going to be useful, and you've got no acid in there, so a pH meter is not going to be useful. Just on the topic of acids, with that reaction that we just looked at, yes, we can use a colorimeter because there is a colour change as the iodine gets used up. But you also have an acid in this reaction. You're producing hydrogen ions, and because you're producing hydrogen ions, you can measure them using a pH meter. You have to have quite a sensitive pH meter to be able to pick up the subtle changes in H+, and which is what it says here. Yeah, whether it's feasible or not depends on how accurate it is. You need to have quite an accurate sensitive pH meter if you're going to use it. But that is another option to to measure the rate of the reaction if it is producing an acid or involving an acid.